I am Ramchandramurthy. I am a co-author of this presentation, DSMC Investigation of Rarified Gas Flow over a Wall-Mounted Cube. The first author is Deepak Navapure, the PhD student at BITS Pilani, Hyderabad campus, India. So a brief outline of the presentation, I'll just give a background of the problem and validation results and the results and conclusion. So to begin with, the rarefied gas flows are basically the flow of gases at very low densities, and that is characterized more quantified by something called Knudsen number, which is the ratio of mean free path to the characteristic length scale. The mean free path is basically the distance the molecule travels before it collides with another one. So based on this value of Knudsen number, the flow is classified into continuum, slip, transition, or free molecular regimes. And the schematic below brief is like it shows an idea of what different regimes are. So in continuum flow, the continuum hypothesis of the fluid flow holds true. That is, we don't consider the fluid as a molecular or particulate in nature. We consider it as a continuum, and all the flow can be studied from the continuum perspective. But as the gas becomes more rarefied, we have to consider the molecular or particular nature of the flow to accurately extract the relevant physics. So there are several applications of rarefied gas flows or where these are encountered. And let me briefly go back. So this Knudsen number can be very high. Then it will be free molecular regime. This can be high if the mean free path is high or if the characteristic length scale is very small. So if you're going into the micro or nano regime, there also Knudsen number can often become large. So if you talk about aerospace application, the flow is already rarefied in the sense that the density of the flow is very less. So the Knudsen number is very high there. And if you go to microfluidics or nano flows, more particularly, there the Knudsen number can be high. So any simulations that we carry out or we study the physics is applicable to both the cases with small changes. So the mathematical modeling of rarefied flows has been done by many researchers using different approaches. So one is using the continuum model where you use Euler's equations or Navier-Stokes equations. And once you enter into the transition regime, we can use more accurately the Burnett equations to derive some analytical results for the rarefied flows. But often these Navier-Stokes equations fail as the flow enters the slip regime, and therefore we have to use Burnett equations, or if it's more rarefied, we have to resort to some other computational tools to study these flows. So the underlying physics behind all this is the kinetic theory of gases, where the particulate nature of the gas is studied and the physical properties are extracted based on the statistical nature of the gas flows. And the Boltzmann equation is used to model the flow for all the flow regimes because it holds for all the flow regimes. But the difficulty is in solving the Boltzmann equation in the desired regime because of interparticular interactions. So in this context, a simulation tool called DSMC method and even the molecular dynamics for that matter can come in handy to solve this stochastically by simulating the flow. So the DSMC method that we refer to in this presentation is a direct simulation Monte Carlo given by proposed by Professor G.V. Bird, and it's a stochastic solution to the Boltzmann equation. It is applied for simulation of flow of dilute gases where the density parameter is small. So essentially the idea is you group certain number of particles or molecules and call it one simulated particle. And you move those small number of simulated particles in the flow domain to extract the relevant physics. So initially we assign the random velocities or positions and velocities. And with time, after a small time step, we move the particles and compute their interactions to the boundaries and also the interparticle collisions. And once we do this long enough, we get sufficient data to average that out and sample the flow properties. So that's the basic idea. So the scope of present study is first we validate the flow solver. So we have essentially used open form solver and the DSMC form that is a part of it, and validated it against a standard benchmark case. Then we have moved on to the rarified flow study over a wall mounted cube, a 2D cube, and we have studied the effect of Mach number and Knudsen number variations. So first coming to the validation of flow over a flat plate, we have taken the benchmark case by where we have experimental results by Becker and others, where the flow of helium over a plate is studied. And we have also plotted the numerical results and compared our results against these two results. So below are the flow conditions of temperature, pressure, and free stream velocity, and so on. So in this graph, we have compared the velocity in the first figure, the non-dimensional velocity. Second figure is non-dimensional temperature, and the last one is the density. So as we see a pretty good match between the numerical experimental results with our results. So whatever you see in the dark solid, black solid line is the present study results for velocity, temperature, and the density. So we see a fairly good match between our results with the published results. So we proceeded with the rarefied gas flow over a wall mounted cube. So essentially this is the flow domain we have considered. We have a bottom wall which has a 2D wall mounted cube, you can say, somewhere 20h downstream. So the first 5h, where h is the height of the cube, which is 3 mm, first 5h is modeled as symmetry boundary condition, and the rest of it shown in red is the wall boundary condition. So the flow enters from left to right. So the left side vertical surface is the inlet essentially, but the left and top surface are both given free stream inlet conditions where molecules can enter primarily, but they can also exit the flow domain. And on the right side, the vertical edge is outlet where the molecules primarily leave the flow domain. So as you see, the height of the channel is 20h, 20 times the cube height, which is sufficiently far enough so that the effect of the bottom wall is not felt at the top surface. So some basic assumptions, we assume that molecules are hard, elastic, perfectly smooth spheres. We have considered non-reacting air and the time step and cell size as per the DSMC guidelines. We have used the DSMC foam, a solver from open foam, and we have modeled the particles as variable hard sphere, or VHS collision model is employed to compute the interparticle collisions. So to capture the variation of Knudsen number, we have modeled or taken the flow conditions at different altitudes. So this is trying to mimic the flow of a re-entry vehicle into the atmosphere. So that's the basic motivation of our study, just to see how the surface protrusions or anomalies on the re-entry vehicles like wall mounted cube can affect the flow properties and aerodynamic phenomena. So for these different altitudes, the Knudsen number comes to 0.05, 0.1, 1, 10, and 20. So these are the values that we employ in our present study. So first, when we vary the Mach number in the first study, we have kept the Knudsen number to 1, which is in the transitional regime, and the wall temperature is maintained as 4 times the free stream temperature. So this is the temperature of the bottom surface or bottom wall for different Mach number. So in the second part of the study, we have looked at the effect of rarefaction, where Mach number is held at 25 and wall temperature is 4 times the free stream temperature, and Knudsen number varies across all the regimes. So coming to the effect of Mach number, so these are the velocity contours for different Mach numbers 5, 10, 25, and 30. So this is a wide range of Mach numbers because Mach number 5 is in the supersonic regime and Mach number 30 is in the hypersonic regime. And as we see, as the flow velocity increases, please note the legends have different maxima. Here the U mean is 1300 and the last figure has U mean of 8000 as a peak velocity. So as the Mach number increases, the effects of the wall are felt are not felt very far away. They're constrained close to the wall. Whereas for low Mach numbers, the effect of wall is even felt larger distances. And the same for the streamlines. But for Mach number 5, we see that flow is more like a laminar flow where we don't have any recirculation at the upstream edge of the cube. Whereas for Mach number 30, we see a recirculation region developing more prominently as the Mach number increases. So these are the pressure contours. Again, please note the maximum of pressure are varying across the flow or the four figures. So in the Mach number 30 case, we see the pressure peaks to a value of 1100, and that is seen primarily at the upstream edge of the wall mounted cube where we have a recirculation stagnation point. And these are the temperature contours similarly, and we see that there are several phenomena that are causing this. First is right near the wall, there's a very high value of shear forces which lead to high value of viscous dissipation. So temperatures are very high here. And again, at the upstream edge of this step or a cube, we have a stagnation point which leads to compressibility effects and therefore high temperature values. And the same trend is observed for all the Mach numbers. The only difference is again, the maximum peak temperature increases with Mach number. So coming to the effect of Knudsen number, here we have the non-dimensional velocity captured across different y locations at these different x locations. So at these four sections, x coordinates, along the perpendicular direction, that is vertical direction, we have plotted the non-dimensional velocity u by u infinity for different Knudsen number. So for all the cases, we see that as Knudsen number increases, that is the green curve, we see that the effects of the bottom wall are felt to a larger distance away from the bottom surface. So that's understandable because the flow is more rarefied and the molecular effects can propagate into the free stream much better than for the continuum flows. And here we plot the non-dimensional velocity along the flow for different Knudsen number. And this we have plotted on the bottom surface. So upstream surface before the cube, and this is the downstream surface after the cube, and this is on the cube's top surface. So we see again more interesting trends here. Well, there is some commonality between all this. That is, for low Knudsen number, we see the more rapid variation of velocity near the wall, whereas for high Knudsen numbers, we see that
2 minutes.
Okay, yeah, thanks. The velocity effects are felt, velocity changes more gradually. And this is the non-dimensional pressure again at different x locations with respect to y coordinate. And we see again that initially the peak right before the cube, the pressure peaks to a very high value, but the peak value comes down as we go downstream. Because again, that's because on the upstream side, the stagnation point exists, therefore we have a high pressure. So this is again pressure along the bottom surface for different Knudsen numbers, and we have non-dimensional temperatures plotted at different sections again. And here also we see similar trend, that is on the upstream surface, the peak temperature has a higher value which decreases as we go downstream. And moreover, for low Knudsen numbers, the peak temperature is even closer to the wall, whereas as the Knudsen number increases, the temperature effects are felt deeper into the free stream in the free molecular regime. So we also extracted skin friction coefficient and the pressure coefficient, and these are the variation along the flow at different x coordinates. And this is also heat transfer coefficient. All these are non-dimensional surface properties we have extracted for different Knudsen number. So just to conclude, the magnitudes of flow properties are seen to increase with Mach number with significant variation among them. And vortex is observed in all the cases downstream of the step, whereas upstream there is an absence of vortex for smallest Mach number. And we see a vortex more developing better for higher Mach number. The variation in flow and thermal properties is by and large relatively similar, with more significant fluctuations observed at lowest Mach number. And for different Knudsen numbers, the velocity profile suggests that at all sections, the near wall velocity is non-zero, except at the sections where the recirculation occurs. Furthermore, the velocity ratios increase with Knudsen number. So in these things, we have also captured the slip velocity behavior of rarified flows near the wall. And the pressure and temperature profiles were found to behave similarly with higher magnitudes near the wall on the upstream phase and attaining free stream magnitudes far away from the wall. So this is understandably so based on the flow physics. With an increase in Knudsen number, the pressure and temperatures increase in the domain owing to viscous dissipation and compressibility effects. So these are the two dominant effects that compete and dictate how the flow contours look like. And finally, the surface properties were found to increase with Knudsen number with peak magnitudes located on the upstream of the stem. So that's basically about our study, and these are some references.
Okay, thank you so much, Ram. I think we have time for a couple of quick questions. If there are no questions, I think we can thank again Ram. Thank you so much for this interesting talk. And we will see here after the coffee break, okay, at 11 a.m. Okay, thank you. And see you here.
Share me. No, I cannot share screen.
Now you should be a co-organizer.
Okay.
Tell me if you are, or let's try again.
Oh, yeah.
I think that now you are a co-organizer, right?
Yeah.
Co-organizer.
Can you see my screen? Can you see my screen?
Yeah, perfect.
All right.
Yeah. Okay, so let me introduce you. The next speaker is Cheng-Gai Sun, and the title of the talk is Enhanced Phase Field-Based Lattice Boltzmann Models for Engineering Applications. So feel free to start whenever you're ready.
All right. This presentation, I will show some recent progress of our team on the phase field-based lattice Boltzmann model. So this is the outline, introduction, phase field model, some validation results, and summaries. Phase field model actually solve two sets of lattice Boltzmann equations. One is for the phase field parameter that tracks the interface of two fluids. The other one is for the pressure and velocity. So phase field has been very successful in free surface flow simulations, which can handle the high density ratio and higher viscosity ratio. There are a wide range of applications of these models, such as tank sloshing, dam breaking, gear lubrication, hydroplaning. The present work will address multi-resolution sliding mesh and removal of some unphysical pressure oscillations. Yeah. So let's take a look at the phase field model. So the first one is phase field lattice Boltzmann equation for phase field parameter phi, which is we consider as a liquid fraction. This is the Lattice-Boltzmann equation for the phase field parameter phi. So here the M is called mobility, is something similar to the diffusivity. Yeah. So the phi is defined of summation of phase field the particle population distribution H I. So the density is defined in terms of phi. When phi equals 0, the density becomes air density. When phi equals 1, the density becomes water density. So, and also the gradient of phi indicate the normal of the interface. So here the equilibrium is considerable two parts. The first part, the phi gamma I is the standard equilibrium distribution. Here we add another second term, theta term, which will introduce a negative diffusion, which can maintain the given thickness of the interface. So, so the theta is a function of the interface thickness W. So eventually, it's equivalent to solve the continuous macroscopic equation of phi. So this is a advection diffusion equation. So here we have a phi term, a theta term. This is a negative diffusion term, which can maintain the prescribed interface thickness. So next equation is Lattice-Boltzmann equation for momentum and pressure. So the G is the distribution function. K is additional force term. So again, the equilibrium first term is a standard equilibrium. The second term of the equilibrium is removal the pressure generated by the gradient of density. So we can maintain a smooth transition of pressure between at the interface. So the first term include several terms. This first term is for the pressure term, for the gradient of density. The second term here is associated with surface tension. Mu phi is actually the chemical potential, which can reproduce the prescribed surface tension sigma. The FB is an external body force. For example, it can be gravity, and also in case of a sliding mesh, it will include the rotation force. So eventually, we define the velocity by the first momentum of the G and plus first term. And the pressure is defined here. eventually it's equivalent to solve the Navier-Stokes equation here. Here, this term is the surface tension term, which will result in prescribed the surface tension sigma. And this is the external body force. So that's the two set of Boltzmann equations to solve. So in our work, we adopt the filtered collision. So the standard lattice Boltzmann equation can be written in this form. This is equivalent to the previous lattice Boltzmann equation. This is the actually no equilibrium distribution. Actually, for the filtered equation, we replace this no equilibrium distribution by a filtered form here, defined here. So the pi is second momentum of the no equilibrium term, no equilibrium distribution, and the h is defined a second order of tensor. So this is a double product of these terms. So this is the filtered no equilibrium. So the filtered collision has some advantage. It has a better isotropy and also has a better stability. So next treatment is we have the pressure correction model. So after the collision, we calculate a delta P, pressure correction term, which is depend on the Laplacian of pressure. And we add this delta P into the pressure and this delta P to the distribution function of G. So this term will remove some of the unphysical pressure oscillation for some cases. Next is the description of the variable resolution. If we have variable resolution, for example, left-hand side is fine, or have fine grid, right-hand side has the coarse grids. So at the overlapping area, we define, we have two sets of lattice is fine, and the underlying we have fine cells. So the first we the underlying layer provide the particles pointing to a fine side, which provide the fine side the particle from this side. So initially we move the particle pointing to fine side onto the fine cells. So this will provide the particles from this side for the fine voxel. And after advection, we are fine box cells will collect the opposite direction of particles, and we collect them into their coarse, we are coarse cells. Then in this way, two sides have the communications. So next topic is sliding mesh. Sliding mesh is very accurate and efficient method for the rotating geometry. The basic idea is initially we have the interior lattice and exterior lattice, which are aligned initially, but the interior mesh will rotate with the geometry. So in this way, the geometry in the local grids is stable. It's not moving. So in this way, the grids rotate with the geometry. So it simplifies the moving geometry. So the at the interface, sliding mesh interface, we define two sets of surface elements. One is for the interior, and the other is for exterior. For example, the solid line and the dash line. Each surface element will talk to pair two opposite surface elements. Yeah, they exchange information and get smooth transition at the interface. That's the basic idea of sliding mesh. So now we have some simulation results. The droplet on the inclined wall, the moving droplets are called VR. Damping case with decay of a cylinder tank and free surface around the submerged cylinder. Okay, let's take a look. So this is a very simple case, a droplet on an inclined wall. So our model, the droplet still in the place and takes developer to that shape. With time, it does not move. This is this case looks like very trivial, but it's quite difficult for some of the two-phase models to simulate. For example, for a Shanchen model, the bubble will move along the wall, cannot stay at the same place. This case without the case do not have gravity, and also in some cases there are some leakage along the wall, so it will form a film along the wall. So for the phase field model, it works perfectly. So next is a demonstration of the variable resolution. So initially, left is cos, right hand is fine grid. So when the droplet move from across the interface, it has a very smooth transition, yeah. And also in the fine, as the droplet move into the fine region, the interface get refined, yeah. So also initially it's in the droplet is in at the center. after 6,400 time steps, it return to the original place. So that's corresponding the exactly preset the flow velocity. Yeah, so let's confirm the Galilean invariance is satisfied. Next is the dam breaking case. Initially, we have water here, and we have some hold on. Yeah, we have the walls.
Okay, time is up. Please proceed with the conclusion.
Okay. So we have the probe here and measurement at the D1, D2, D4 locations. So here shows the shows front position. It compare well with same experiment, and also the water head at a different location. So reasonably good with experiment. This one is the pressure. This is experiment the pressure at these 4 locations, and here is our simulation pressure. We have also simulated with refined region here, the same problem, same setup, but with refined region here. So basically, we got similar results. So this is a single level of the grid. This is a 2 level of the resolution. So the simulation get very similar results. So next one is
we don't have time. Please proceed with the conclusion. We're running late.
Oh, all right. Okay, this is a simulation of the tank sloshing case. Yeah, okay, it's hold on. This is a submerged cylinder. Okay, we present. So let's jump to the results. We have this drag coefficient, lift coefficient, relatively well compared to the experiment. Then the last one is the rotating cross with the water at the interface. We have the very smooth transition of the fluid bubbles. So the conclusion, we have smooth transition of the free surface across the VR interface, and we have a smooth transition of interface across the sliding mesh. So pressure oscillation treatment can reduce the pressure oscillation, and we have relatively good agreement with the experiment for the submerged cylinder and also for the tank sloshing case. Yeah, that's thank you for your attention.
Okay, thank you so much. Okay, we have a question. I can read it from Christophe Corexas. What are the stability limits of the proposed approach in terms of density ratio and Reynolds number?
Currently we have the density ratio 1000. Yeah, it's reasonably stable. For the Reynolds number, we have a few thousand, depending on the cases. So roughly tau equals the viscosity we can reach about 0.005, something like that. Yeah.
Okay. A second question, which is the last one. How do you realize the conservation of the momentum? It is mentioned in the paper published in 2018, but not clear.
Yeah, eventually, actually, we can achieve the Navier-Stokes equation, right? Hold on, let's see. Yeah, actually, the momentum equation is we can eventually achieve this kind of Navier-Stokes equation. So the momentum conservation is guaranteed. Yeah, here.
Of this presentation, Hiroshi Otomo. So momentum conservation is here the guarantee only when the surface tension is zero. Otherwise, it's not conserved.
Guys, I think that we should skip to the next speaker. If you want, you can discuss it.
Okay.
Okay, if it is okay.
Okay.
Okay, so thanks again, Shanghai, and let's skip to the next speaker, which is George Vahala. Let me enable you as a co-organizer. Okay, George, now you are a co-organizer, so you should be able to share your screen. Give me a sign. George?
Yes.
Ah, okay, perfect. Hi. Okay, you should be able to share your screen. So, first of all, I present you. So the next speaker is George Vahala, and the title of the talk is Quantum Lattice Algorithm for Maxwell Equations. So let's start whenever you're ready.
Thank you. We're presenting our work on...
We don't see the screen, actually.
I'm sorry?
Actually, I cannot see your screen shared.
Apologize.
Yeah, take your time. Okay, perfect. Now I can see. Perfect.
Sorry.
Okay.
So we're going to present work we're developing on a quantum lattice algorithm to solve Maxwell's equations and then applying it to plasma physics. And the idea basically is, can this then be run on a quantum computer, eventually error correcting? And in the back of my mind also is that, will this quantum lattice algorithm be more efficient than the classical algorithms for solving Maxwell's equations? So here are our Maxwell's equations. That's our dielectric constant, E electric, B magnetic fields. We use the Kahn representation in terms of what they call polarization vector. And using the F vectors, you can rewrite Maxwell's equations in terms of an 8-spinner. The reasoning behind this is to see the similarity between Maxwell's equations and Dirac equations. And from then on, you can develop your quantum lattice algorithm. So this is the 8-spinner, where the psi plus, psi minus are the components of the F. The M matrix is the Pauli spin matrix tensor product, the identity. And one can see that if you have a homogeneous system, then the dielectric constant is a constant, and then the off-diagonal terms are 0, and then psi plus, psi minus uncouple. And then you've got basically the two polarizations. So the idea behind it is, if you're on a homogeneous medium, psi plus, psi minus uncouple, and defining your psi plus is this 4-spinner, 4 qubits, this is then in your normalized units, the differential equation you want to satisfy. And one notices that this is extremely similar to the Dirac equation for a massless particle. And Yepes in 2005 has developed a quantum Laplace algorithm to solve the Dirac equation. So with that, we can now try to move on to looking at inhomogeneous media and defining basically the unitary, if possible, collision operators and streaming operators so that in the long wavelength limit, you recover Maxwell's equations. So if you look in the 1D homogeneous medium problem, where say the refractive index is a function of X, these are your 8-spinner equations. And so we now have to devise a collide stream algorithm for the derivative term and for the inhomogeneous term. One notices that first, let's look at the inhomogeneous term, the derivative term. We see Q0 couples to Q2, Q1, Q3, 4 to 6, 5 to 7. So that means that the collision operator will couple 0 to 2. There's the coupling 1 to 3, etc. So that's how you can devise the 8x8 collision matrix. And theta is your collision angle, and the choice of it will depend, of course, on the coefficient in front of the derivative. And we introduce a small parameter epsilon because it's a perturbation theory. The streaming operator we do in steps when we have this interlining of the collide stream. And so we will stream qubits 0, 1, 4, 5 at one instance in the sequence, and then the remaining 4 in the other sequence. So this will then lead us to looking at the inhomogeneous term. And here we see again Q0 is coupled to Q1. So let's just couple to these components first, and that's a 0-1 coupling. There's a 0-1 coupling, etc. You then have to work out what your relaxation angle is, if you want to call it that. And it's dependent on this n prime, the derivative of the refractive index, and we choose the order epsilon squared. And similarly, to recover the coupling term, you couple Q0 to Q6, so there's Q0 to Q6. And then you just finish off the matrix. So then it's a similar collide stream algorithm that you have seen in lattice gas methods. There's the adjoint of the collision stream, collision, inverse stream, etc. These operators do not commute. If they did, then you would be an identity. And so you evolve your 8-spinner qubit Q of t by the following sequence of operations. And then if you go into the long wavelength limit, you will then recover the Maxwell equations for 1D inhomogeneous systems to second order accuracy. So here's some results. This is looking at propagation in the z direction. We've done various pulses. This is for hyperbolic secant pulse. We're looking at vacuum into a refractive medium N2, which peaks at 1.5 back to a vacuum. And it's a sharp interface, but continuous. So the boundary layer is 40 units. The pulse width is 800 lattice units. So initially, as you're propagating the pulse in our units, the E field, the EX and the BY fields are equal. So they're superimposed. You now hit the interface. At the interface, you'll get reflection and you get transmission. In the transmitted, the E field, B field have different amplitudes, different widths than the initial. And as you learned in your standard E&M course, if you are reflecting from low to high refractive index, it's the electric field that will change phase by pi. The blue curve is the E field, the red curve is the B field. And they have equal amplitudes as they pull out. Now, this pulse will hit the back of the dielectric, this region here, And so you're now going to get also transmission and reflection from here. That's what we see. This is the initial reflected pulse. This is the reflected pulse from here. At this stage, because you're going from high to low refractive index, it's a magnetic field that will change by pi. And sure enough, that's your red curve. And then this will do another reflection transmission at this point. So we're recovering basically standard E&M. We look at conservation of energy, the instantaneous Poynting flux, E cross P dot N. N is the outward normal. And the only part that's awkward, you see these jumps. And these jumps are basically when the pulse is straddling the two regions of the dielectric. Because when it straddles, you have to be careful in trying to figure out what's basically traveling forward and what's being reflected to get the right the right outward normal. And the first time we went through it, we didn't bother trying to be careful, and so that's why you get these bumps. So we clarified that by doing another problem where you go from refracted index 1 to 2. We will take this to be like the midpoint of our transition layer. And now we look at a particular time where the pulse straddles the two dielectrics. And this is the electric field from the simulation. That's a total electric field. This is in blue, the total magnetic field. So all you have to do is that the final field is nothing but the vacuum or the initial field and the reflected field. And so you can just determine what the vacuum field is. That's just propagation of the pulse. And so you just subtract the two, and then you'll get what the reflected. And if it's a reflected, then you know the normal is in the minus C direction. And if it's the vacuum field, it's in the plus X direction. So doing that for the E field and B field, you will then find that you get excellent conservation of Poynting flux. You don't see this dip. So what we've been able to verify is that we recover all of the plane wave properties of reflection transmission. The only thing novel is that the transmitted electric field is greater than the incident electric field over that of the plane wave by the square root of N2 over N1. And we verified this for different pulse geometries, different choices of refractive indices, different perturbation parameters epsilon. And then we've now developed a theory for Gaussian profiles, Gaussian pulses, that in fact show that you should get this square root of N2 over N1. All the other properties are to like 4 figures being satisfied. So now we move to 2D, and in the 2D quantum lattice, it's nothing but the tensor product of the X propagation and Z propagation because they're in Cartesian coordinates. So initially we're going to have a pulse that's now going to be propagating, in this case, to cone, dielectric cone. And so initially there's just an EY and a BZ field, and they're 1D because the function is just of X. When you interact with the 2D cone, you'll start developing 2D characteristics. If the gradients are weak,
Ja, und ich muss dann halt im Grunde sagen, entweder ja, das ist noch untersucht,
du
kannst auch ja, das ist interessant, das muss ich probieren.
Genau, du kannst auch sagen, dass
Sorry, Georgia, can you please activate your microphone?
Okay, does that do it?
Yeah. Okay.
Okay, sorry. So here we have the pulse propagating. This is when it starts to interact with the cone. And then this is the wavefront that you get emitted from the dielectric region if it's weak gradients. And So then we've also looked at the stronger cylinder dielectric, going from 1 to 2 quite rapidly. And what you'll see is very complicated wavefronts being emitted. And that's because you're going to get reflections within these dielectric regions, just like we saw in the 1D. In very low gradients, it's like a WKB, where you just basically just have one pass. And that's why you see the simple. And this is showing it in detail, like what's happening within this dielectric cylinder. So we're just looking purely in this sort of region. This is that the pulse starts to interact with the dielectric. The phase velocity decreases within the dielectric, and that's why you see the concave structure. It now starts to be basically focused into this end here, and that's why you see the blip coming up. And then you see the reflected, then you see the blip, and then reflected back. So you get this backward forwards. And you also, of course, get a negative electric field. So this is to give you what you also see in 1D, that the E field polarization can change. Also, you'll generate in 2D, you'll now have to, for div B being 0, you have to generate a BX field, and we do that, we recover that, and it's got a dipole-like structure. So this is what the BX field looks like after, say, 30,000 iterations. And 30,000 iterations is basically this stage right here.
2 minutes.
Thank you. And div B, again, it's a dipole-like structure. It's fairly low. And then once you see the interactions, like 2 orders of magnitude below. So basically what we've done is we developed a quantum lattice gas for Maxwell's equations for a scalar dielectric. Doing initial value code, there's no boundary conditions applied except the end conditions being periodic. For 3D simulations, we'll only need 16 qubits per lattice site. And the epsilon parameter that we've had to introduce is basically nothing but the normalized speed of light in the vacuum. And what surprised us is that the QLA algorithm is stable all the way to epsilon equals 1. And we're going to be extending this to tensor dielectrics and eventually go to the cold plasma dispersion relation. And finally, here's a movie of this pulse propagating against the cylinder dielectric, the sharp. And so around 16, there's the interaction. These spikes are basically due to, I think, the focusing of the beam in the corners of the dielectric cylinder. Okay, thank you.
Okay, thank you so much, George. And if you have a question, please write it or raise your hand. Okay. If not, thanks again, George, and we proceed with the other speaker, with the last speaker, which is Klimak. Let me allow you to share your screen. Organizer. Okay, Martin, can you hear me?
Yes, I can. I just have a problem turning on my camera at the moment, but oh no, now it works. Okay.
Okay, and can you share your screen? I think now Georgia is okay, perfect. No, this is still the, I don't know. Okay, now Martin is
now?
Perfect. I can see it.
Okay.
So let me introduce you. So the next speaker is Martin Klimak, and the title of the talk is Investigation of Airflow Around Gable Roof Houses Using the Lattice-Boltzmann Method with Kbc Collision Operator. So proceed.
Yeah.
With, okay.
Then hello to my talk. The title has changed a bit, but now it's Investigation of the Influence of Gable Roof Shape on wind loads using the Lattice-Boltzmann Method with the Kbc Collision Operator. And currently there's no paper on this yet, since it's basically the results of my master thesis. So there will be hopefully coming a paper in the coming month. Why don't you switch? Okay, so just to motivate the whole thing, here's like one of the possible results of turbulent airflow around the roof, and basically damage to the roof. And this, probably on a bit smaller scale, happens to about 900,000 houses in Germany per year. So this is, of course, an important field of study, or an important application of the simulations, in order to find out how to reduce damage to houses and avoid this kind of stuff. And from the residential buildings, single-family homes are the most common variety, and the most common type is the one with gable roof. So I'm focusing on that in this work. For a bit of context, the state of research, of course, there have already been some investigations about houses with gable roofs. There's an investigation in the stationary airflow around different shapes of houses, and also an investigation on the influence of the roof pitch on the structure of vortices and the velocity field around houses. Yes, so now in this work, new is the focus on the pressures on the roof, which then, of course, result in the, for example, the suction that sucks away the shingles from the roof and are therefore the actual cause of the damage. And I want to specifically focus on the influence of the roof pitch and possible, or the roof overhangs on these pressures. And since I'm using the Lattice-Boltzmann method in comparison to the previous unspaced investigations, there's also the advantage that it's easier to look, or there's better possibilities to look at transient values, and therefore also investigate the fluctuations and spikes in the pressure. Yeah, for the rest, since we already motivated and talked about the state of research, I want to introduce my use solver, then the simulation setup, before I come to some verification against a reference to make sure the whole thing is valid, and then present my results and conclusions and give a short outlook on what's to come. Yeah, my use solver, I used the solver Lattice, which is developed here at the University of Applied Sciences Bonn-Rhein-Sieg. And it has the advantages that it's written in Python, so it's easy and fast to use, for example, for rapid prototyping. But it's also based on PyTorch, so it supports CUDA hardware acceleration, and it also allows to combine Lattice-Boltzmann method and machine learning, which will be demonstrated, for example, by Mario Bedronka in his upcoming talk, Neural Lattice-Boltzmann method for machine learning enhanced simulation. And yeah, if you're interested, you can check it out here on GitHub. To come to our simulation setup, so first we have our simulation domain, which is of course constructed by the boundary conditions with the house inside that's being investigated. And so first of all, we have our inlet boundary, which is a non-equilibrium extrapolation boundary that of course prescribes the microscopic velocity and extrapolates the density from inside. And then the flow passes by the house and can leave either to the top or the back of the simulation domain. And on top, we have a zero gradient boundary, mostly for its compatibility with the neighboring boundaries. And that's supposed to simulate the open atmosphere above. And on the back side, we have an equilibrium boundary that's, of course, then prescribing the density as average and taking the microscopic velocity from inside, so the fluid can leave the domain uninhibited. Then we have periodic sides, and our house and ground, so the solid obstacles basically are formed by a bounce-back boundary. On the inlet, I'm using this typical exponential velocity profile to determine the wind speed depending on height. And as you can see, the standard, or the standard velocity is always at the height of the ridge of the roof. And then we have our investigated shapes of the house. So we have 10 by 10 meters and a ridge height of 12.5 meters, which is constant for all versions in order to always cover the same part of the velocity curve. And then we have, of course, the three different investigated roof pitches, so 20 degrees, 35, and 50 degrees. And here we can also see what is meant by roof overhang. So basically that the roof is hanging over outside basically the wall. And in order to find out what influence that has on the pressures and so on, There was also another version of the house where it's basically without the roof overhang. So it's just this corner basically. Yeah, then the simulation parameters were chosen to be as realistic as possible, of course, with the physical parameters of air at 15 degrees Celsius and 1 atmosphere of pressure. And we were able to reach a Reynolds number of 20,000, which is sadly quite low in comparison to a realistic storm with damage potential. That's more on the order of 10 to the power of 7. And we used a D3Q27 lattice or stencil for its better representation of turbulence in comparison to D3Q19. A Mach number of 0.1 and managed to fit about 15 million lattice nodes in one NVIDIA V100, which gives us a lattice constant of 18 centimeters and a time step of 0.3 seconds. And as I said in the title as well, we're using the Kbc Collision Operator, which is an MRT collision operator. And it works by decomposing F into the different moments. So we have the constant ones, and then we have the second order moment and the higher order moments. And the second order moment is treated just with tau, so like BGK, whereas the higher order moments are relaxed using this gamma, which is an entropy optimized relaxation time. And this provides increased stability and good accuracy on under-resolved flows in comparison to BGK. And then to verify, of course, figure out if this whole thing is representative of reality, we're comparing against the wind tunnel measurements of Tominaga et al., who were also investigating the airflow around gable roofs of different pitches. So, of course, for the comparison, all the parameters were changed to fit their parameters as closely as possible for maximum comparability. And here we have the comparison for the relative flow velocity. So in the central plane, basically, of the simulation domain along the x-axis. And here we can see that the simulation results in black do agree quite well with the wind tunnel measurements of the reference in gray. Which is also shown in the average relative error of 8%. Then we have to look at the pressure coefficient as well, which is just the difference of the local pressure to the reference pressure divided by the dynamic pressure of the inflow. And here we are looking at, again, the pressure along the cross section of the house. So we can have our windward wall here in blue, the leeward wall in yellow, the windward side of the roof in green, and the leeward side of the roof in red. And of course, the simulation results again as a line, and the wind tunnel measurements as the dots. And here, of course, we can see that there's less good agreement here, especially for the flattest roof. We have a relative difference of about 59%, so quite large. That gets better as the roof pitch rises until it's at about 28% for the steepest roof here. This problem or this low accuracy is a bit offset by the fact that we're later looking at a bit steeper roof at 50 degrees, 35 and 20. And we can also see that already here at the 26-degree roof, we can see that there's at least qualitative agreement between the results. So for example, here we have this steep decline and then this shape, and here it's the same for the simulation results. And here we can quite clearly see the qualitative agreement, which is also the reason why for now we're focusing mostly on qualitative interpretations of the results. Then the results and conclusions. I want to first look at the flow pattern at different roof pitches, then the pressure on the roof surface at different pitches, and finally the pressure on the roof surface with and without roof overhangs to determine their influence. And here we can see in this plane, we will look at the flow pattern, and along this line, we will look at the pressures on the roof. Here we can see an example shot of the house being in the airflow basically, and all the turbulence it causes. So here we have the so-called horseshoe vortex, And then we have all the vortices that form behind the house, visualized by the Q criterion and colored by velocity. And yeah, then the influence of the roof pitch on the airflow pattern. Here we can see that whereas here, of course, is the horseshoe vortex again, which is very much the same for all of them. But we can see that between 35 and 50 degrees, there's quite little changes. Whereas in between 20 and 35 degrees pitch, there's quite a large change from having just one large vortex to several smaller ones, which leads to believe that there's some kind of a more drastic change in the behavior between a roof pitch of 20 and 35 degrees. And we can observe a similar thing for the wind loads on the surface at different pitches. So we're looking at the average standard deviation and the minimum of the pressure coefficient. And here we can as well see this grouping of the behaviors. So we have the more steep roofs having a positive pressure on the leeward side, windward side, whereas the flatter roof has suction here and also stronger suction on the leeward side, and also way stronger fluctuations or higher standard deviation, especially starting at the ridge, and then which also goes hand in hand with stronger pressure minima or suction maxima, which also leads us to conclude that the flattest roof is the least suitable to withstand the wind we are investigating, since it has the strongest fluctuations and suction out of all of them. And then from the group of steeper roofs, we can see that the less steep roof at 35 degrees has lower pressure on the windward side and also lower fluctuations near the ridge, which leads to the conclusion that the medium steep roof at 35 degrees is probably the most suitable to withstand or gets the lowest wind load from the investigated airflow. And yeah, which also leads to suspect that there might be an even better roof in between 20 and 35, just after the drastic change in behavior. Then to look at the influence of the roof overhang, we can see the average of the pressure coefficient at 20 degrees, 35 and 50, each a comparison with overhang in blue and without overhang in orange. Here just a short reminder what I mean by roof overhang. And here we can see that the influence of the roof overhang increases as the roof pitch increases. So we have quite a large difference and then barely any difference at 50 degrees. And then at 20 degrees pitch, we can see that having a roof overhang on the one hand reduces the suction on the windward side of the roof and also reduces the fluctuations on the leeward side and the ridge, and also reduces the suction maxima or pressure minima on the leeward side of the roof as well. Yeah, we're running a bit out of time. So for 35 degrees roof, we can see very similar results of the or influence of the roof overhang. So basically we can conclude that the roof overhang helps to improve the load or lower it. And yeah, a short outlook, what's to come. The plan is to get to a higher resolution by implementing parallelization in order to have a larger simulation domain and therefore be able to simulate at higher accuracy and Reynolds numbers, and also to implement Bender boundary conditions in hopes to be able to interpolate the location and not have the staircase on the roof anymore, and also a higher order of boundary conditions. And then finally, of course, it would be interesting to investigate further directions the airflow is coming from, since of course wind doesn't just come from one direction in the real world, and to investigate more roof pitches and maybe find the optimum and yeah, investigate more roof shapes like chimneys and the likes. Yeah, thank you for your attention.
So thank you so much, Martin. Okay, we have a question. Read. Could you comment on the use of the D3Q27 lattice as compared to the 19 counterpart for a better representation of turbulence? This does not seem to be in agreement with what is done in the industry for high Reynolds number flow simulation. This is Christoph, which is asking.
I can actually it's, as I said so far, it's mostly the results of my thesis, so I didn't have that much time to investigate everything. So this choice is mostly based on literature I found. Yeah, so I cannot comment currently, but I will have to investigate if maybe the using D3Q19 might actually result in better results. I'm sorry, I can't can't elaborate much here.
Okay, perfect. Other questions? No, I have a question. Is this code implemented in Python, right?
Yes.
Even okay, so all in Python, and this optimized for CUDA. I mean, did you profile this code in terms of I mean, performances, gigaflops and so on?
Not extensively, but it's running at, I think, like 60 million lattice updates per second. So it's not that fast, but because of the CUDA optimization that we can use thanks to PyTorch, it's still not that slow as you would maybe expect from a PyTorch Python implementation.
Yeah. I see. Okay, there is another question. KBC formulations usually suffer from dispersion issues at moderate to high Reynolds numbers. Did you observe this issue in your simulation? So sparse vortices appearing in the shear layers, for example?
I did not specifically. However, I still need to investigate the whole thing a bit more. So it's mostly just, yeah, I'm hoping to get to higher accuracy and yeah, investigate everything a bit more further. So maybe I will, if I find some, I can contact you again.
Okay, perfect. So if there are no questions, I think we can conclude this session. Thank you so much, Martin, and thank you to all the speakers. I think that now there is the lunch break, and then we will update at 3 p.m. Okay, thank you so much again.
Thank you.